So now I'd like to do an example of using the integral test. And I'm going to try, as we get into examples now, to remind us what we do know. What are all the things that we could possibly do? So I don't want to just assume that I know it's the integral test, because part of what you'll need to develop is a strategy. It's one thing to know how to figure out if a geometric series converges, or use the properties, or telescoping, or integral test. It's another to be able to look at the series and decide which approach you're going to use. So as we're going through this, you might want to keep a separate sheet in your notes where you're just keeping track of ideas, thoughts, decisions, how you're making your decisions about which approach to use. And I'll try and emphasize that as we do examples. So here's a series, natural log of n over n from 3 to infinity. So we know about geometric. Now remember, geometric will look like a number to the n, or maybe a ratio of numbers to the n. Could be n minus 1 or n plus 3. But everything's to the nth power, right? And that is not happening here. So it's just visually does not appear to be geometric. What else do we know? Nth term test. Well, take the limit as n goes to infinity of natural log of n over n. That's actually theorem 5, tells us that goes to 0. And we kind of know that intuitively, right? We know that polynomials grow faster than logarithms, so that should go to 0. So that's inconclusive. Remember, nth term test, no good if it goes to 0. Doesn't tell us anything. The properties, well, those were all about breaking it up or factoring out. And there's nothing to really, I mean, we could write that as the series of natural log of n times 1 over n, but there's no theorem about breaking up a product, right? It's only a sum or difference or taking out a constant. So properties don't do us any good. The useful facts don't do us any good. And it's not telescoping, right? Telescoping looks like a function minus itself, just shifted by 1, and it's not that either. So just process of elimination, none of the things we've seen so far would really work on this. But let's think about the function. Let's think about the corresponding function here, f of x, natural log of x over x. Now, let's remind ourselves what the theorem requires. Over the interval we're looking at, that thing should be positive, continuous, and decreasing. So I don't need you to prove that, but I need you to state it when you make your argument. You should be confirming that in your head for yourself or in scratch paper. I don't need a proof, but you don't want to do integral test on something that's not positive, decreasing, continuous. So let's go through those. Positive, well, we're only looking from 3 to infinity. Natural log is positive from 1 on, right? At 1 it crosses the axis, right? Let's just think about that. And x is positive when we're starting at 3 and going to infinity. So that ratio is positive. I can confidently say that. What about continuous? Well, natural log as a function we know is continuous over its whole domain, which is x greater than 0, and we're going from x greater than or equal to 3. So that piece is continuous anyways. And x is continuous. It's just a line. It's continuous everywhere. The only place this would really have a chance of being discontinuous is in a divide by 0 situation. But again, we're starting at 3. So that thing is continuous. We're past any problem spots on that. The trickier one might be decreasing. A couple ways you can go to convince yourself that that's decreasing on our interval. One is to just think, well, natural log of x grows much, much slower than x. So we know that this goes to 0, right? And it's positive. So it's probably downward, right? It's not 100%. That's just a loose argument that it must eventually be decreasing, right? There's nothing oscillating going on there. Natural log goes up, x goes up faster, so in the ratio it goes down. If you weren't sure, you could use what you know from Calc 1, right? We know that if it's decreasing, that needs to be less than 0, right? A negative derivative tells you decreasing function. So you could do that. If you weren't sure, you could take a look at the derivative. We got to do quotient rule. So derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. And we want to know, when is that negative, right? A negative derivative means a decreasing function. So when is our function decreasing? Well, the bottom of this is always positive. So the only time this fraction is going to be less than 0 is if the top of the fraction is less than 0. And the top of the fraction is 1 minus natural log of x, or natural log of x greater than 1. Well, when is natural log of x bigger than 1? Well, when x is e, it equals 1, right, by definition. And then after that, it's bigger. So we're looking for x is bigger than e, and e is somewhere between 2 and 3. So it's not an accident that this is starting at 3. It's starting precisely when we need it to start so that everything works out nicely. So we know that as long as x is bigger than e, which it is because it's starting at 3, the function is decreasing. So you don't have to prove this to me, but you do have to convince yourself that you're using it in the right place. So all I need to see from you in your argument is that. If you need to do some work to convince yourself that it's true, that's okay. Now what? Now that says we can proceed with the integral test. So what I need to do is take the improper integral, and let me add on here, just so we're clear, positive, continuous, and decreasing. Add this in there as well, because this isn't always true, right? It's where we're interested, and it's on the interval from where we're going to look, 3 to infinity. Those things are true. Other places, right, this is not true. When x is negative, well, it isn't defined, but when x is between 0 and 1, that thing's negative. So we just got to be careful that we really should be specific. So add that on there to what I want to see. Now, let's do the integral. So now we just have to investigate whether or not this integral converges or diverges. And remember, first step in an improper integral is to make it proper. So we're going to take the limit as b goes to infinity of the integral from 3 to b, natural log of x over x dx. And now we have to think about how we integrate that. Well, what should hopefully jump out at us is the derivative of natural log of x is 1 over x, and so u substitution. And so our integral is now from don't forget our limit. The limit as b goes to infinity of natural log. Remember to switch your limits. These are x limits, so natural log of 3 to natural log of b. And now just u du. And that is the limit as b goes to infinity. 1/2 u squared. So 1/2 natural log of b squared minus 1/2 natural log of 3 squared. Well, this is just a constant. This is the only thing this guy is changing as b goes to infinity. And we know natural log goes to infinity, so natural log squared is just going to infinity even faster. So this whole thing is infinity. So what did we just establish? We just established that this integral is divergent, so I want you to state that. So since the integral from 3 to infinity of natural log of x over x dx diverges, then that tells me that the series n from 3 to infinity of natural log of n over n diverges by integral test. All right, so first you look at the corresponding function on the interval that we're summing there from 3 to infinity. Is it positive, continuous, decreasing? Yes, it is. You just need to state that. Don't need to show me. Take the integral. Whatever the result is, the behavior for the series is the same. So this came out divergent. And again, avoid pronouns. Don't say it diverges. Be specific what you're referring to. The integral diverges. That tells you that the series diverges by the integral test. Now, an important thing to think of is if this had converged, say this equals 6, that doesn't mean the series equals 6. It just tells us the series converges because it's less than that, really. Or at least in the argument, it's that it's below, right? But you don't know that that's what the sum is. But you can use the integral to say something about what range that sum could be in. And we'll talk about that later. But in the convergent case, the series and the integral don't have the same value. But if the series converges, the integral converges. Or excuse me, if the integral converges, then the series does. Just not to the same value.